Okay, we need to talk about the properties of working with exponents. And you learned these back in middle school, but we really need to retain them, and sometimes we don't. So let's go through them once again. Now, the first four that we look at right here, these are the ones that you have learned previously. And we're going to look at an example that involves a base of a each time and derive a formula that we can use with any situation. When I have something like a to the second times a to the third, I want you to take a moment and think about what that means. That means I have a times a would represent a to the second times a to the third. So when you multiply that out, we've got all the same base. So a times a times a times a times a, we could represent as base a to the fifth power because there are five of them. When we're working with exponents, we get confused about when to add our exponents or when to multiply our exponents. If we'll just stop for a moment and think about what the problem is showing us, we'll always remember the right operation. So a to the second times a to the third, it's very easy for us to know that that's 2a's multiplied by 3a's. And we know that exponents always mean how many of that base are you multiplying. So when we write it out, we have no question that what we should have done here was add our exponents. Now the generic rule, how you'll see this written that doesn't involve any numbers, we'll often see it written something like x to the a power times x to the b power is going to always equal the base x raised to the a plus b power. Okay? And it's very important that we remember this rule. But what's most important in mathematics all the time is that we don't forget what we know we know. We know what exponents mean, and we can derive any answer from the knowledge we have in our heads. So don't get bogged down in, oh, I don't remember that rule. Everybody knows what an exponent means, and we can get any answer from that. So a to the second raised to the third, I want you to think about what that means. We've got a to the second 3 times. So that means a to the second times a to the second times a to the second. We interpret what that problem means. Now, if I can remember that previous rule, then I should know here that what I'm supposed to do is add those exponents. But if I didn't, I can write this out. A to the second 3 times means I'd have 3 groups of a to the second. Which gives me a to the sixth power. Okay? And there was no question about me knowing what that rule was because I know what that problem or that expression means. Now, as a generic rule, this will often be written as x to the a raised to the b is always going to equal x to the a times b power. Because our shortcut would have been to remember to multiply those powers together. But if we did not remember our shortcut, we got that problem correctly just through the simplification and knowledge of what an exponent truly means. So a to the third divided by a to the second, we're going to write this out. We know that a to the third, and everybody knows that a to the third means a times a times a divided by a to the second. So when I have a factor on the top and that same factor on the bottom, we know that they do divide evenly. We get bogged down a lot of times in saying they cancel each other out. They do cancel each other out, but you need to know the operation that's occurring, and what's going on is they're dividing each other, leaving me with the value of 1. Now, I'm not writing the 1 because I've got something else there holding its place, so it's not necessary for me to leave a 1 coefficient. But a to the third divided by a to the second leaves me with a, which is the same thing as a to the first power. We understood that power to be there. So my shortcut here that my rules are trying to tell me is that when I have, let's say, x to the a power divided by the same base raised to a different power, my shortcut would be to subtract those powers. Keep my base, x, but subtract the top exponent minus my bottom exponent. And it's wonderful and grand if I can remember this shortcut. But if I cannot remember that shortcut, I simply remember what an exponent means, and I can get my problem right every time. Okay, a to the third divided by a to the second, all raised to the fourth power. That means we should see that fraction occurring 4 times. So a to the third over a to the second, I'll write it 4 times. And then I can write out a to the third 4 times on the top. That would leave me with a to the 12th. I'd have 12 of them if I wrote out 4 groups of a to the third. On the bottom, I'd have a to the second, a to the second, a to the second. I'd write that out 4 times. That's a to the 8th power. So if I ended up with 12 a's on the top, this is just too big of a number for me to write out, so I'm going to attempt to apply my shortcut here, thinking about what these exponents mean. I have a to the 12th over a to the 8th. Using that shortcut, I can subtract 12 minus 8 to give me a to the 4th power. So that problem kind of involves two of our rules here. And most of the time our exponent expressions do that. So let's just summarize here. If I had something like x to the a power over y to the b power, and let's say I have that whole quantity, what that didn't look like a parentheses, raised to the c power, my shortcut is telling me that I can multiply and raise the top to the c power, which would be x to the a times c, and on bottom, raise y to the b also to the c power, which would be y to the b times c. I'm raising the numerator and the denominator to the c power. Now, 2 new properties that you learned in analytic geometry, are a to the 0 power. And that answer, anything to the 0 power is always 1. That's a rule we tend to remember because it's such an easy answer, but it's also important that we understand where that came from. If I was going to think about what would precede something using these exponent rules to get a 0 power, I'd have to have something like this, a to the third divided by a to the third, or a to the fourth over a to the fourth, or a to the fifth over a to the fifth. Because if I apply these rules, I know I'm going to subtract these exponents. That leaves me with a to the 0 power. So if I think about the kind of problem that would have come before a to the 0, for me to get an answer of a to the 0, doesn't it make perfect sense that those 2 terms would have had to divide each other out for me to end up with a power of 0? Therefore, it makes sense why our answer to the 0 power is always 1, because this quantity had to begin being something divided by itself. We also learn in analytic geometry about negative exponents. We learn that when I have a negative exponent, we need to simplify that by moving the location of the base. Right now, this problem is a to the negative 2 over 1. So if I've got an issue with a negative exponent, which I should always have issues with a negative exponent, I'm not going to leave them in any expression, I need to move that base to this opposite location. If it's negative in the numerator, I need to move it to the denominator. If it were negative in the denominator, I'd want to move it to the numerator. So when I take a to the negative 2 and I move it to the denominator, the minute I move that exponent of 2 across that fraction bar or that division bar, my exponent becomes positive. Now, the 1 that was already in the denominator is still in the denominator. It's the coefficient of a to the second now, but it's not necessary for me to write it. And there is a 1 left in the numerator because by the same standards, there is an invisible 1 in front of that a to the second. A lot of times with negative exponents, we think we're flipping locations. Like what was on the bottom automatically moves to the top. That's not what we're doing. We're looking for any base that had a negative exponent, and we're moving the location of only that base. So my generic rule here would be maybe a base x to the negative y power. We would rewrite as 1 over x to the positive y power. Okay? Now, these exponent rules need to be like second nature for you. You should know these automatically. They should just be right there in your brain when you need them. You've used them a bunch in your life, and when there's something that we cannot forget.